Okay, I won't keep you too long today. A little bit more about this last example. When using the upwind method, he has shown here, yes, indeed, you get the first error terms as diffusions. So you have it there. Next topic in the book is solving linear equation systems, which then also will be our jump. We will have more about finite volume later, but I will jump into the fast solvers now. But today I will only have a peek at it. You have been given some material. Here. Finite volume we're done today. So the next topic we start with multigrid. This is just some handwritten notes by Årset. But they're quite okay, and a little bit too much more than we need, but they're okay to follow. Then also I will afterwards look into Krylov methods, Krylov being conjugate gradient methods. So these are sort of the choices that you have today when looking into fast solvers. Also, of course, you have direct methods. But in practice, for big problems, you can't use direct methods. You blow the memory in any computer. So you are left with an iterative scheme, and then it will typically be either multigrid or Krylov. And I believe that a user of CFD, he should be familiar with these methods. You should know when your computer code asks you what different parameters are you going to put into your multigrid version. Then you should know what they're talking about. And conjugate gradient methods, then which one should you use? What should you do for preconditioner, stuff like that. So yeah, you should be aware of some details here. After we have done then with the fast solver part, shouldn't take too long actually. We will continue then back to finite volume, unstructured mesh, and then finally we have turbulence. Also, under reference, if you want to have a start, you have a free book by Briggs, a multigrid tutorial. That's a very neat little book if you want to have a quick introduction into multigrid. And a lot of the material that we are going to go through are stolen from this book. So that one I can really recommend. For now, I just wanted to actually repeat something you have seen before. And that was, where was it? This example here. Yeah. Let's just try to run it. It was the example I used with SOR, successive overlap relaxation. And here it's just a solution of a Laplace equation, double derivative equal to 0 in both directions. So initially you start everything equal to 0, and then you have one boundary, the one here. Here you have given the value of 1. And also on the back wall here we have the value 0, so they are constants. Here it's derivative equal to 0, and here derivative equal to 0. So Dirichlet conditions and Neumann conditions. And to solve it, using finite difference central scheme for the double derivatives, you got something like this, one which shows a very good omega. And here is a 100 by 100 unknowns. And to find a solution pretty fast, you need an omega very close to 2. Omega should be between 1 and 2, and the more unknowns you have, the closer he should be towards the value 2. So now it's 1.98, I think. And you see also what he does. He sort of enhances the adjustments a little bit too much, so it can be quite violently sort of shaking a rug really, really hard. Now it's now 1.99, just to see the effect there. So as an overall solution algorithm, the SOR is very easy to program and works quite fast. So typically this will be the first one you try. It's so easy to program. But you're going to need a lot of iterations in the end to find a good solution. And of course, if you can recall, if you go back to omega equals 1, then it's what's called a Gauss-Seidel iteration. Then you're in trouble. Gauss-Seidel iterations are very slow. They take forever to find a solution. So here you see nothing much happens from one iteration to the next. And he's way off in the end after 500 iterations. And of course, using omega smaller than 1, say 0.6 as an under-relaxation, yes, you can do that, but why should you? Now it's even slower, so this is going to take forever. So it's a very, very bad idea. But what was interesting with these Jacobi and Gauss-Seidel iterations, the way I programmed it now, it is Gauss-Seidel. I overwrite my unknowns during the iterations as the calculation goes. I don't store it in a temporary matrix. So hence this is what we call Gauss-Seidel. If you want Jacobi, then everything on the right-hand side should be from the previous iteration. Here it's going to be a mix, since you are inside a loop. So that's Gauss-Seidel. If you want an omega bigger than 1, you have to do Gauss-Seidel. Jacobi will explode. He doesn't make it with omegas bigger than 1. Then you can't over-relaxate at all. But back to these old traditional classical methods, Jacobi, Gauss-Seidel, and give the initial field a random generator. So now I have omega 0.6, and the initial fields looked something like this, very messy, everything between zeros and 1, and then we start to iterate. Then you see a lot of things happen in the very beginning of the iteration sequence. The first 10 iterations, he does a lot. But now he is extremely slow. So, and we are still far from the solution. This point is actually more or less correct, 0.5, sort of an average of the random numbers. But this plateau here is flat, and that's not correct. So it should be curved all the way. So it's very, very slow now if you wanted to have the correct solution. Now using random numbers as initial state and going back to the optimum omega for an over-relaxation, 1.98, you'll see the difference. The high-frequent noise lives much, much longer. But still, in the end, this algorithm is more effective. He finds the solution very nicely within 500 iterations, more or less. So much more efficient. But not in the beginning. And that's the whole point with multigrid. So now the idea goes as follows with multigrid. Say go back to an omega 1 or something, 0.7, whatever. And then we step through the first iterations. This is the initial field, total noise. Make one iteration. So you see practically all that noise has been halved, I would say. And then another one. And then another one. Now we have 3. Say 4. 5. Now you see not that much happens from one iteration to the next. So from here on, he is not efficient anymore. He has been very efficient so far, reducing all that high frequent noise, but this wavy pattern here is going to survive for a very long time. You're going to need many iterations to get rid of them, and finally to get the overall smooth solution. Then he is terrible, but he's good at removing high frequency noise, this very violent behavior. But from now on, he is very inefficient. So the idea with multigrid is, why not use this simple, classical, old-fashioned method to what he is good at? So if we now had taken the solution we have here, transfer it to another mesh, which is, say, you only use every other points in both directions. So that would be only 1/4 of the original problem. Then this motion here, this wavy, nice, smooth motion, is going to appear more high frequent on a coarser mesh. So transfer this one to a coarser mesh, and then you do some iterations there with this old classical stupid method. He's going then to do the same as what he's good at. You only need a couple of iterations to filter out the high frequent noise. And then you could actually transfer it to an even coarser mesh. You can have several mesh layers, coarser and coarser, and then use the same idea. Sooner or later, then, when you have the solution, you have to nest your way back up again to the finest mesh to obtain the solution on the fine mesh. Of course, that's what we want in the end. But the idea with multigrid is just that. Use or take benefit from what these classical methods are good at. So here, if I now go back to the optimum omega, 1.98 or whatever it was, and if we now step through the first iterations, you will see not much of a change actually. He seems to be just as noisy as the initial state. Actually, he has done something. Take a couple of more iterations. Here, now we have 10 iterations. Still looks very messy indeed. But if you flip it around, so he has started at least to soften down this area here, because here you have a boundary value of 0, and here you have the boundary of 1, constant values. So the solution is sort of going to spread out, or the smoothness of the solution is going to spread out from these two edges to cover the entire domain, but it takes long time. So an optimum omega, big omega, yes, that's more efficient if you are only using this method, but it's not efficient if you are talking about multigrid. So then we should have a small omega. If you want one smaller than 1, of course, that's your choice, but 1 or 0.7 or something is widely used around there. So here now you see we have reduced the higher frequent noise to more low frequent. So that is the philosophy behind multigrid. That's what we are going to have a look into next time. And you have been given some material. You don't have to read it in advance. It's not that tricky. So this is then what we are going to have a peek into. This multigrid concept can be done extremely complex if you look at the numerical theory behind it. It is not easy to take. Some of these books that are listed in the reference here, they are pretty scary. If you are interested in math, be my guest, but they're very tough indeed. But actually you don't really need it. This cute little book by Briggs covers it quite nicely. So as engineers, we are only interested in something that works. We don't actually need to know the details why it works. So I won't go into the tough math to describe the method. That's too heavy. If you want a quick and dirty setup, you have been given this compendium, the Navier-Stokes solver. Here then I implemented multigrid into the Sola algorithm. And the first part, I think I referred to this one already. We have looked into the stability here, max-min method, and also we have gone through the projection method, the time split method. And here you find description of the classical methods, Jacobi, SOR. And also line Jacobi and line Gauss-Seidel, they are a little bit different, sort of the same idea, but you use the Thomas algorithm, the solution algorithm for a direct solver when you have a 3-diagonal matrix. If you take a 2-dimensional or even a 3-dimensional case, and then you say along one single line, I have my unknown, straight through the domain, only along that line. Everything else I assume is known. Then you can write your equation system as a 3-diagonal system and solve it directly. Then of course you have to take the next line and the next one and sweep across the entire domain. So that is what a line solver is. But it belongs to the same family of classical iterative methods. Still is used a lot in multigrid as well, together with Jacobi and Gauss-Seidel. But then here, a quick short description of multigrid, how I implemented it in Sola, and some test cases. So you can actually find something there. Let's just jump down to the classical methods. From the projection method, solving the Navier-Stokes, the transient Navier-Stokes, we got the Poisson equation for the pressure, or actually the pressure difference, beta equals 1 normally. And the right-hand side is given from the divergence of this tentative velocity field. So this is the elliptic equation that we are going to solve, setting it up with finite difference, and then using the modified Newton-Raphson, you can get Jacobi and Gauss-Seidel schemes like this. So if you program it without thinking, you will get Gauss-Seidel. You will typically then have a mix from freshly updated values and some from the previous iteration versus Jacobi. Here everything should be from the previous iteration, finding the value for the new iteration. Then you have to use some temporary storage somehow. And SOR, that was the modified Newton-Raphson. You just multiply with an omega, you overdo the adjustments, and normally that works fine, but sometimes you actually have to under-relaxate if the equation system becomes unstable, like you saw in this example from Verziger in chapter 4. The line solver, you just choose one line and say, these are now my unknown. And since it's a double derivative, you only have 3 unknowns equal now to the right-hand side. And here, inside here, you will have then the other neighbors that is missing in the other direction, of course. But you will end up with an 3-diagonal equation system like this. Diagonal will be -2, something with the boundaries, of course, and then another bond, which then can be solved using a direct method, like the Thomas algorithm. So no problem there. So there you will have the full 5-diagonal system. Of course, this one also could be solved if it's not too big, solved directly. But we are focusing on iterative schemes. I also took into account here a little trick. If you are using cyclic or periodic boundary conditions, all of a sudden you get a coefficient in the corners. The rest of for this matrix is going to be 0. And how to handle this one with a simple direct solver? Yes, you can do that. It's a little trick. You skip the last row and the last column and solve this one first, and then you have to do a little trick to get this included. But that's only for cyclic and periodic boundary conditions. So here I now have compared the different methods. I just invented sort of an analytical solution and created a problem. So given some cosine in both x and y direction. So I know the solution. And initially now I start with just a random field. So here is the correct solution. Initial field, total random numbers between plus minus 1. So now you solve that one using the different methods. Here you have Jacobi. That is where you had to do some temporary storage, only use old values when you create a new iteration. Gauss-Seidel, just a direct programming. SOR with an optimum omega, close to optimum. And then this line solver, Gauss-Seidel. So you see, after one single iteration, what's happened? The classical methods are filtering out the high-frequent noise. The SOR is not. Even after 1, 2, 3 iterations, you still have a lot of noise here. In the end, he is the most efficient. After 20 iterations, clearly he's going to win, finding the solution fastest. These other methods, they are very fast in filtering out the high-frequent noise. But they are going to be terrible in finding the correct solution here. They're going to take forever to achieve it. Also this line solver as well. But you see what they are good at. For the first 2, 3 iterations, all this high-frequent noise has almost disappeared. So especially here, Gauss-Seidel and also this line Gauss-Seidel, now it looks very smooth indeed. So that is what we are going to use in multigrid. That's the philosophy behind multigrid. Use these old-fashioned methods to what they are good at. And if you want to have a peek, you can then look in part 2 how this is done. So here you'll find a sort of a very quick description of what is multigrid. Here, of course, I have focused on what I need for the Sola algorithm. So it's sort of one version. but you can have a look at it if you want. I just want to show you the end result here, which is quite nicely. Here I have tried to solve the equation system using different mesh and then of course different number of internal cells. And then I have used as many different grid levels in multigrid that I can. Then I have plotted here the number of cells, which then will be the number of unknowns, versus how many operations is needed to find a solution. And you see for the different cases, they fit pretty close to a straight line, indicating that yes, multigrid is capable of solving a problem with n unknowns with order n operations. And that's the only method capable of doing that. Conjugate gradient will be a good number 2. Here you can make it, it's going to be a little bit curved upwards. He will be of order n times log n, I think, or ln n. So multigrid sort of supposed to be the fastest, yes. That's true with modifications. Here is a Poisson equation, linear, nice, no problem there. I have a nice rectangular cell systems, more or less. So then he is very close to the optimum, yes. In a general problem, then it's a question. Then multigrid maybe not so fast, and furthermore, not so easy to implement. We'll come back to that later. The problem here will be you have several mesh systems, coarser and coarser mesh. How can you use that to describe complex geometry? And what about the boundary conditions? You need boundary conditions for all these different mesh systems. That's complex. But that's something we are going to address then during multigrid. Okay. So then you have an idea what's coming. Any questions? I think we had the right room tomorrow, didn't we? Yeah, because now we are not in week 8. That's next week. Yeah. So we have share number 4 tomorrow. So I'll meet you there. Then we stop here.